Welcome back, guys. So as we said in the previous video, the differential of a work is equal to the scalar product of F dot dr. And from here, guys, comes the good news of the principal work and energy that is not a vector equation, instead it's a scalar value. So the work is a scalar because this is the scalar product of the force and dr, which is always a scalar value. And I know that the kinetic energy is scalar because it is equal to half mv squared. Any vector squared is a scalar value. So I know, guys, right now that du is equal to f dot dr, which means it is equal to the dot product between the force and the displacement vector. And what is the dot product between f and dr? It's in fact f, the magnitude of f, times the magnitude of dr, which is ds, times cosine theta. So guys, if I take a look on this equation, I am saying that du, which is the differential work, is equal to the product of f times ds cosine theta, which is what? Which is the projection of dr on the line of action of f. So this is the projection of dr on f, because of course this is the perpendicular line, this is here at 90 degrees. So the projection of ds on this force here is ds cosine theta, and it's equal to this distance right here. And of course, guys, theta will be the angle between the force and this dr. What does this mean? This means, guys, that the work is equal to the force times the displacement on the line of action of this force, which also means if the force is perpendicular to the displacement, there's never going to be any work of this force on this particle. And you can see this from the equation of dot product. Whenever I have a force that is perpendicular to the displacement, the angle between them will be 90, cosine theta will be 0, and then the work will be 0. Which means, guys, a force that is perpendicular to the displacement is not going to have any work. In fact, it will not cause any displacement. And this also means, guys, that a force that is collinear with the displacement will have a maximum work, because in this case theta will be equal to 0 and then cosine theta will be equal to 1. Now, so far I am talking about du. So if I want to find du between position 1 and 2, I should do the integration, which means u12 will be equal to the integration of f dr, f dot dr, which is the scalar product. Now what does this mean? What does this equation mean? The work between position 1 and position 2 is equal to the integration of f dot dr. Can I remove f from the integration? In fact, I can only remove f from integration if f is constant with respect to what? With respect to the position. In other words, if f is independent of the position, then I can say that f is constant with respect to position. And then I can remove this f from the integration. So in order to do this, let's substitute f dot dr by its equation in a scalar product, which is f ds cosine theta. And let's take the case where f is constant. So as I said, guys, if f is constant with respect to the position, then f could be removed from the integration. And in this case, u12 is equal to f integration of cosine theta ds. If theta is also constant with respect to position, so f is also maintaining the same direction with the displacement, then I can also remove cosine theta from the integration. And in this case, I'm going to have f cosine theta integration of ds. So I'm gonna repeat, guys. If f in magnitude is constant, if the angle between f and ds is constant, then I can say that u12 is equal to f cosine theta integration of ds. And what does this mean? This means that u12 is equal to f cosine theta delta s, s2 minus s1. So guys, if f is a constant vector, the work of this force on this particle will be equal to f cosine theta s2 minus s1. I'm going to ask you a question, guys. Where can I have a constant force? It is, in fact, the weight. The weight, guys, is a constant force, which means I can say that the work of the weight is equal to the weight itself, cosine theta delta s. Right? So the work of the weight could be also W cosine theta delta s. But I should, guys, find out what is the sign. Is it a plus or minus? What does this mean? If the work of the force is positive, then this means that the displacement projection on this force, on the weight, is in the same direction of this weight. Which means, guys, if delta S projection on the weight is downward, because the weight is always downward, then I can say that this work is positive. If delta S projection on the weight is upward, then I can say that the work of this weight is negative. Now, guys, if I want to get rid of the sign and don't think about it, I can transform the work of the weight in Cartesian form. So I'm going to replace the force F in vector form into Cartesian form, which is in fact minus Wj because the weight is always downward. And then I'm going to replace the r by dxi plus dyj plus dzk. And then I'm going to do the dot product between these two quantities, these two vectors in Cartesian form. I know, in fact, that the vector I know that the dot product of two perpendicular vectors will be always equal to 0, which means j dot I will be equal to 0 and j dot k will be equal to 0. So these terms, guys, will vanish. I will only have this term and this term. So what is the dot product of minus wj dyj? In fact, the j dot j is equal to 1, and then the answer will be the integration of minus w dy. And since w is constant, then I can remove it from the integration, and then this will be minus w y2 minus y1. So in this case, guys, I can directly know the sign. It is always minus w y2 minus y1. Alright? So either, guys, you use this equation where you have to think about the sign, or you can use this equation, the work of the weight in Cartesian form is equal to minus w y2 minus y1. And you're going to have the same answer. Why? Because in fact, if y2 minus y1 is positive, then this means, guys, that the particle is going upward. Now, if the particle is going upward, the projection of this displacement will be in the negative direction of the weight because it's always downward. And then, since this is positive, then the weight, then the work will be negative, and this is what we will face here. All right? Now, if y2 minus y1 is negative, then this means, guys, that this particle is going downward in the same direction of the weight. This is negative times a negative value will be positive, and this is what you're going to have here, plus w cosine theta delta s. So, guys, you're going to have the same answer, right? So, you're going to have the same answer if you do it either in w cosine theta delta s, and here I forgot to put absolute value of delta s in order to put a plus or minus sign, and or you can do it using this equation minus w delta y, where delta y is y2 minus y1, and in this case you're not gonna think about the sign. It's automatically minus WY2 minus Y1. Now, how to choose between them, how to choose which equation is correct for the work of the weight? In fact, guys, it depends on the given. If you know the angle between the weight and the tangent at this path, then you have to use the first one, and you have to know if it is a positive or a negative sign. Now, if you have the coordinates of the point at S1 and S2, you should use the second one, and in this case, guys, you're gonna have a minus WY2 minus 1 minus Y1, which is where the sign is given automatically. Now, guys, in the next video, we're gonna do the work of the spring. Thank you.